Indeed. Okay, good. Well, thanks for this introduction. Let me also start by thanking the organizers. It's really a great pleasure to attend this program, this workshop. The last program which I attended in KITP was the one which was organized in 2020, which was fully online for obvious reasons. So I'm really glad to attend this new program now in person, which is quite a different experience. Good. So the purpose of this talk is to introduce a class of models of active matter, which are very much inspired by the behavior of some biological tissues. And what I would like to show you in short is that these models reproduce the emergence of waves of local contraction, which can propagate in dense environments, and which can organize into various dynamical patterns that you can already see here, which leads to quite a rich phenomenology, which I would like to introduce today. So first, let me start by emphasizing that the tissues that motivate these works are the ones where you can neglect the flow of material. So in other words, I will assume that you can, in particular, safely neglect the self-propulsion of the cells, and I will assume that the only source of activity here will be the periodic contraction of cells in the tissue. And if you want to think of concrete examples of such tissues, you can, for instance, consider the case of cardiac tissues, where here the local contraction of cells leads to waves which propagate and which essentially regulate the periodic beating of our hearts. So indeed, when the heart beats, it corresponds to a wave which is triggered at a specific location shown here, and as you see, propagates over these two ventricles to contract them in a specific order in order to pump blood through the heart. So if you have the same heart and if you record an electrocardiogram, you'll find the signal shown here in blue, where you see sharp pulses which are separated by a well-defined period. And then for whatever reason, the heart may deregulate. And when it does so, as you see, it goes through a series of stages. And when it reaches this final stage, which is called fibrillation, you find out that the pulses are much weaker. And actually, they are so weak that they can no longer contract these two ventricles. This is why the heart stops beating. So if you are a physicist, you will find that arguably the most interesting regime of the heart is actually this one. And a simple way to realize that is, for instance, to measure the phase voltage at the surface of the tissue, which is a proxy for measuring the local contraction. And indeed, if you measure the phase voltage during fibrillation, you'll find this sort of map, which is obviously very rich. And if you are a physicist, you'll find that there are specific points, which here are highlighted in red and green dots, which corresponds to topological defects. But actually, these defects have an autonomous dynamics, and this is why I call this a defect turbulence. These defects are spontaneously created by pairs. They can move in the tissue autonomously, and if you find defect of opposite charges which collide, they will merge and annihilate as you would expect. So in short, I'm trying to argue here that cardiac tissues are really a very good example of a biological system where there is a clear connection between some diseases in the form of heart rhythm disorder and the formation of dynamical patterns, for instance, defect turbulence. And this means that for physicists like us, it's an interesting challenge to try and propose minimal models which somehow capture the emergence of such waves and which could be used as a platform to understand how you can control the various patterns in which these waves organize. For instance, this would inform concrete strategies to destabilize the defect turbulence and therefore find a way to help the heart recover a sane rhythm after a heart attack. Okay, so for today, I would like to show you that indeed we can reproduce the emergence of such waves by regarding these tissues as a dense assembly of active patterns. But importantly, I will assume here that the only source of activity is what I will call the pulsation of the cells, which is essentially an internal clock, which will lead to periodic deformation. And I would like to show you first that if you combine this individual pulsation with some well-chosen ingredients, you are able to capture the formation of waves, and I would like to show you that we can actually study in great detail the transitions which lead to stabilize these various patterns. All right. So then from this particle-based model, I would like to show you that we can actually also propose a hydrodynamic description, either by coarse graining the dynamics or rather by postulating the hydrodynamics with a few ingredients. And in particular, I would like to show you that from these hydrodynamics, we can actually try to understand the patterns into which these contraction waves spontaneously organized by looking at the statistics of some specific defects. I would like to show you that there is this connection between defect statistics and the patterns which emerge for these waves. Good. Okay, so let me start therefore by introducing this particle-based model of pulsating particles. So I would consider repulsive particles in 2 dimensions, and I will track their dynamics in terms of their positions, and also in terms of what I will call internal degrees of freedoms, which are the faces of the particles. And as you see here, the size of a given particle, sigma I, is determined by its phase, theta I, so that when the phase varies, the particles will deform. Right? In all what follows, I will assume that you can simply color the particles according to their sizes so that you can easily identify waves in dense environments. So we postulate here that the dynamics is essentially a set of overdamped Langevin equations. In particular, you see this first equation for the positions is exactly what you write down for a purely passive system. Right? In particular, I would assume that this potential here is repulsive, but also short-range and pairwise, which means that it depends on the interparticle distance, xij, scaled by the sum of the radii, sigma I plus sigma j. Okay, so this is so far equilibrium physics. So now I will introduce a few non-equilibrium ingredients. So the first one, as you see here, is a drive. And it tells you that even in the absence of interaction, every particle will act to expand and contract. It does so periodically, and for simplicity, I will assume that the period is the same for all the particles. Second non-equilibrium is this one. This is a synchronization term, which has a finite range, and because the connectivity of the particle depends on time, this is actually a non-equilibrium ingredient. And the final term here is a potential term, which is things you would expect just because the potential depends both on position and on phases. Okay, so in particular, if you would like to compare the effect of this potential term with this one, you can, for instance, consider a case where 2 particles overlap with one another. You will find that this potential term will lead to contract the particles at fixed positions. That potential term will lead to move them at fixed sizes, right? And I would like to show you now that these 2 non-equilibrium ingredients are sufficient to create waves. All right, so let's start by trying to identify the regimes where the waves emerge in this minimal model. So to do that, I introduce here 2 order parameters. One is quite standard. This is just quantifying the proportion of particles which have the same phase at a given time. This is a current, which will be useful as well, and you see it's scaled here in a way that essentially the current is 1 if all the particles cycle at their Bayer frequency. So we record the average values of these 2 parameters when you change the density of the system and the strength of synchronization. And when you see this phase diagram for the first time, immediately you realize that there are 2 regimes of parameters where the system orders. You see here at high density, you have clearly an ordered state, and it corresponds to a vanishing current. So I will call this an arrested state in what follows, and I will try to tell you why this arises there. Another ordered state which arises here has now a current, so I will call this a cycling state. Okay, so 2 ordered states, 1 cycling, 1 arrested, and if I look at carefully what are the trajectories for these 2, you'll find indeed they are very different. So on the left, we have this cycling state. All the particles are changing their sizes in synchrony. This is the global change of color. And in contrast, you see at high density, you have this orange background. This corresponds to the case where there is not enough space between the particles. Particles can only grow up to a certain size, and then they will fluctuate around this size. Okay, so we have here 2 ordered states, no waves so far. And what I would like to draw your attention to is that perhaps the most interesting feature of this phase diagram is that these 2 ordered states here and there are completely disconnected. So this means that if you would like to go from arrest to cycles, for instance, by decreasing the density, you have to go through a region of disorder. And I would like to show you now that this regime of disorder is exactly when you see the emergence of waves in the system. Okay, so for instance, the sort of waves that you could see there have this form. They are corresponding to defect turbulence, again, which mirrors what we saw in the fibrillation of cardiac tissues. But interestingly, you can also see that as a coexistence between arrested particles and on top of that, cycling particles. And what you see very clearly is that these local excitations actually organize due to the nearby synchronization so that you see these waves propagating in the system. So these are clearly contraction waves in the sense that on timescales where the wave propagates, the particles actually barely move. They are not associated with any flow of material. So if you look at more carefully at the profile for these waves, you'll find that actually At both ends of each wave, you can find a pair of defects, right? So if you integrate here the phase around this closed contour, you'll find a defect with either plus or minus 1 charge. And if you do the same operation at the other end of the wave, you'll find a defect with exactly the opposite charge. So what I would like to argue throughout this talk is that you can actually regard the dynamics of these waves as being effectively driven by these defects forming here. Okay, so this is defect turbulence. And this arises here, close to the resting state, if you decrease a bit the density. So now if you would like to decrease even further the density, what you see is that you reduce lower and lower the order parameter, right? This is just because there is more and more space between the particles, so more and more particles are prone to cycling. And interestingly, when you are deep in the disordered state, what you'll find now is that these waves can organize in length scales which are of the order of system size. And now you could see the emergence of various types of patterns. So let me show you 2 of them. So for instance, you could see here a spiral wave on the left, where instead of having a sea of motile defects, you see I'm left with only a single pair. Now here one at the center, the other at the edge. And if you look at carefully the profile of the phase around the defect, you will find that here the profile is actually symmetric, so that this defect is no longer motile compared with the previous case. Another case that another type of wave, I should say, that you can find in similar regimes is here a circular wave. And in this case, you can see there is still here a defect pair. But if you were to wait longer, you'll find that these 2 defects will merge and will annihilate. So in steady state, this is actually a defect-free solution. There are other solutions. There are, for instance, planar waves. So in short, there is quite a rich family of waves which form in this particular part of the phase diagram, which again is here in the disordered state, exactly in between arrest and cycling. Okay, so what I would like to argue from now on is that although this model is quite rich, we think it's actually only one model of, I want to say, one instance of a broader class of models. And an interesting challenge is to try to derive hydrodynamic equations from this specific model, and then to identify generic features from these hydrodynamics, which we think is shared by a broader class of models. So this is something that I think many of you are familiar with. You start from the microscopic equations of motion, you coarse grain, you use approximations, and you arrive at hydrodynamics for a finite number of fields. So here, the field of interest is the complex field defined here. And as you see, the equations that we get is essentially an expansion in powers of this field and is graded. And in particular, because we coarse grain, we know that the coefficients here, A and B, are complex numbers, so that you could regard this equation as a variant of the standard complex Gizmo-Landau equation. But what is interesting here is that you have these extra terms here, which are shown in green, and what these terms do is that they break the rotational invariant. Right. So in other words, if you didn't have these green terms, if you were only interested in this part of the dynamics, then you could rotate the phase by an arbitrary amount. It would leave the equations invariant, and this means that for the standard complex Gizmo-Landau equation, essentially all the realizations of phase have the same status. We have these extra terms which break this invariance, and there is actually a simple piece of physics here. It's just because in our case, the phase represents the local sizes of the particles, and particles repel with one another, so you realize that an assembly of small particles cannot be equivalent to an assembly of big particles, right? So it's actually not a surprise that at the hydrodynamic level, you have to have these terms which tell you that there are some realizations of the phase which play a specific role here. So if you would like to understand what this does to the dynamics, you can, for instance, consider the case where the system orders. So when the system orders, you can write down a closed dynamics for the phase. And as you see here, it's essentially a competition between the drive and a landscape, which is set by the repulsion between the particles. All right? And you can try to rationalize this competition. You can, for instance, consider the case where the density is higher than the critical value, and then you'll see that this landscape has a series of minima. So this will correspond to a rest in a regime where the repulsion is dominant over the drive. In contrast, you can consider the case where now at low density, the drive is dominant over the repulsion. You no longer have any minimum, therefore it will create a current in the system. Okay. So what is particularly interesting is that with these equations, you can actually find a regime of density which is close to the critical value for which there is an instability which rises and which mirrors what we saw in the particle-based model. So specifically, you see that there are here patterns in the profile of the amplitude which lead you to identify some defects where the amplitude is close to zero indeed. If you look at the profile of the phase, you'll find that, for instance, here, you see clearly there is a spiral which forms around these defects, very much like what we saw in the particle-based model. Okay, so hopefully I've convinced you at this stage.
One question. In your equation on the top, you write plus noise.
Yes.
So the regime that you call arrest, will you get arrest in the minimum and then activation and motion and so kind of intermittency in your wave dynamics, or how would it look like?
Thanks, Julien, for the question. So what I call arrest is really a regime of vanishing current. But any amount of noise could, in principle, lead to a rare event where you could have, let's say, nucleation of the point, which will create, for instance, this sort of transient cycling, but this will vanish very quickly. Maybe what is interesting, building on your question, is the fact that you see, in order to, so this is very much a Milford picture, and in order to create these patterns, indeed, the noise is very crucial, right? So what you find is that it's really when you are close to the critical density, where essentially you have still a local minimum, but now because of the noise, you could activate transition, which corresponds here to a jump from this minimum to the next, right? And the mechanism, indeed, which creates these waves is basically noise-activated event, which corresponds to this jump, and this requires the barrier to be low enough, which means basically close to critical density. Yes. So short answer, you need a noise to create these patterns, and you understand it as basically transition from here to there associated by the noise, right? And interestingly, you could try and compute, for instance, the instanton, which leads you from here to there, and this is actually a route where we want to explore to, for instance, look at the profile of the phase around the defect. Happy to discuss that further, but okay, maybe this is pushing us a bit too far at the moment. Any other question? Okay. So if not, let me move on. So this was the first hydrodynamics which I wanted to introduce to you. Essentially, complex Simpson-Landau equation without gauge invariance. What I would like to argue is that, although this is quite appealing, it completely misses the fact that when you have waves in the profile of the phase, you should expect to have also waves in the profile of density. And actually, these hydrodynamics will not capture that because it completely discard the coupling between the deformation of the cells and their displacement. So I would like now to propose a revised hydrodynamics which explicitly couples density and phase. So instead of deriving it, I will now postulate the hydrodynamics with a few arguments, and I hope to convince you that this is enough here to capture the physics at play. All right, so let me start by assuming that you can regard this system as a liquid, which means that I will assume that I can, in particular, write the balance of momentum, as you see here, when neglecting inertia as the balance between a dry friction and a force coming from a stress tensor. And in a very simple description, I will assume that the stress just has a pressure contribution, which is given here by the derivative of this free energy with respect to density. I can combine the three lines into a single equation for density, which I'm sure many of you would have perhaps done directly. And now I have to postulate the shape of the free energy. So to do that, I will assume that essentially the free energy shown here penalizes deviation of density from a reference value. And importantly, I will assume that this reference value is modulated by the phase field, which, as before, will represent the local internal degrees of freedom of the particles which compose the fluid. So at this stage, this is, I would say, quite a broad formulation. I don't describe in details how the particles deform. I could, for instance, consider the case of an assembly of hexagons, as you see there, whose size is controlled by a single scalar value. But what is really important is that I have in mind confluent configurations. And indeed, this means that, for instance, if you have a location of the system here where you see the particles are bigger than their surrounding, this will lead to local displacement. And at the coarse grain level, this means that whenever you have a modulation of the phase, it will come with a modulation of density, right? And this is exactly what this captures, which tells you that the density will locally adapt to the reference value set by the phase. Okay. Yes?
Are the higher order terms unimportant?
So I will argue that they are indeed unimportant, yeah, let's assume that we can build the simplest theory, which is basically a power law expansion in rho and in the simplest mode of psi, which is just time psi here. And let's see if this is sufficient. Okay, so I still need to complement this equation with an equation for the phase. And I will do so again by assuming that there are three main ingredients. You need here a drive, the internal pulsation, then you need a synchronization, which will lead to homogenize the phase profile. And you need a mechanical feedback between phase and density here, which is written in terms of the same free energy as the one which appears in the density dynamics. Okay, so this is arguably the simplest sort of theory just for two scalar fields that describe compressible liquids with internal degree of freedom, which are driven. And in particular, you see that if you let the drive vanish, the system relaxes towards an equilibrium configuration, which just minimizes the free energy. And in this case, it's actually a homogeneous configuration. Okay, so when you put a drive, you will recover again this trade-off between the free energy landscape and here the tilt. Again, at high density you arrest, at low density you cycle, but because now you allow both density and phase to be modulated, it's actually more relevant to consider how the tilted landscape behaves as a function of the phase and the density. And what you see clearly here is that if you go towards higher values of phase, and if you locate a series of minima for the free energy, you'll find that the density actually oscillates, right? And hopefully at this stage, I've tried to convince you that this is exactly the physics we want to capture, which tells you that when you have a wave which will increase the phase, it will come with oscillations of the density. So waves of phase will come with wave of density. This is what we want to capture here. Okay, so let's try and understand what is the regime where the waves appear. So again, we can resort on these two parameters, synchronization and current. We can look at how they are changing when you control the density of the system and the drive. And you'll find that at high density and low drive, the system arrests. So this means that the system orders in a regime where the current vanishes. So far, so good. At low density and high drive, the system cycles. So it orders, but now with a higher current, as you would expect. Interestingly, in between arrest and cycles, as we saw previously, you have patterns, right? And let me show you now that these patterns correspond to wave where both the density and the phase are being driven. Okay, so you see these waves. On the right, they are waves of the phase. Hopefully, you can distinguish that these waves, again, are excitation on an arrested background, right? So the arrested background here will correspond to the green colors, and you have this excitation which can propagate. But interestingly, with this excitation of the phase, you see that you have here also modulation of the density around the average value. So if you look at more carefully at these waves, you'll find that there are specific locations where they are triggered, which we call pacemakers by analogy with the heart. And I would like to draw your attention to the fact that these pacemakers actually have a specific structure in space, which is set by the early instability. So in particular, if you start from a homogeneous configuration, you can show that the first instability that kicks in is actually a spiral instability, which will lead to a modulated density, which is what you see here on the left. And when the modulation of density exceeds a certain threshold, you will find that waves are triggered. And once these waves are triggered, you find that they are self-sustained and they can keep propagating in the system. Okay. But again, the important thing is that here, these pacemakers have a structure and organization which is reset by the early spinal instability. Okay, so I would like to argue that these are really contraction waves. And to do so, to argue that this is not only modulation of density, I would like now to focus your attention on the profile of the velocity orientation. Right, so this is just defined by conservation of mass. You can define here a current, which indeed is just the velocity at which the particles are displaced. And what you see very clearly is that there are defects which appear in the profile of these waves. And specifically, you see that there are asters here, which form exactly at the same location as the one of the pacemakers. Right. And if you look at the profile of these asters, you'll find that actually you can have this configuration here where you see essentially the particles are moved outwards, okay, but you also have this configuration where instead the particles are moved inwards, right? And because this is a dynamic picture where the waves will be triggered periodically from these pacemakers, you'll find that periodically the particles will be either pushed outward or inward, which is indeed what you expect from a contraction wave. Okay, so what is quite interesting is that there are here quite a lot of defects, and I would say there is actually a hierarchy of defects. There are the ones which are obvious to detect, which are here at the center of the asters, right? But there are all the defects which are perhaps less obvious. You have, for instance, this one, which corresponds to the point where the wave will coalesce. And you see, for instance, also in between the asters, you here have quite a lot of defects. So we'd like to have a systematic way to locate this defect and potentially to study their dynamics. To do that, we resort on a recent proposal by Luisa, who gave a talk this morning, and which is itself inspired by earlier work by Halperin and Mazenko. And the idea is essentially to define a field which is here given in terms of the gradient of the velocity, in a way that if you integrate this field over a domain which contains a defect, you essentially pick up the charge. So the idea is to go from a description of defects in terms of point-like objects to a description of extended field which picks up the charge, okay? This is what we call the charge density, and indeed what you see is that if you look at the behavior of the charge density, you pick up not only the obvious defects which are at the center of the asters, but you also have here a lot of defects, for instance, in between these asters, which are present there, and I would like to show you that these have quite a rich dynamics. Okay, so if you look at the dynamics here on the bottom left of the velocity orientation, indeed you see you have these asters, clearly, which periodically will point outward and inward. And if you now look at the charge density, you see that there is what we call a hierarchy of defects, in the sense that there are defects which have a long relaxation, or here, which are basically have a long lifetime, which was the one at the center of the asters. But interestingly, you see that as the wave propagates, you have also periodically a lot of defects which are being created and annihilated. And you could, for instance, look at this defect more clearly. And okay, here also a lot of defects which are related to the formation of these waves. Okay, so this is very much work in progress, but hopefully I've convinced you that if you are able to characterize the statistics of these defects in the profile of the velocity orientation, for instance, by looking at the distribution of lifetime, the distribution of velocity, you can somehow try to understand how the pacemakers interact with one another and potentially try to say something about the organization of these waves. Okay, so I would like to conclude here. I hope that I've convinced you that pulsating active matter is an interesting class of models of active systems. This was very much inspired, as I said, by the behavior of contractile tissues. But we think actually there is a broader class of systems which share a similar phenomenology. To capture this phenomenology, you need three main ingredients. You need a drive, right? But instead of driving the displacement of particles as you do in motile active matter, here we drive some internal states which regulate interactions between the particles. You need a local synchronization which will promote order. And finally, you need an arrest mechanism which can compete with synchronization and drive to yield patterns. But importantly, this arrest mechanism is indeed the important ingredient which will break the rotational invariance at the hydrodynamic level. So most of the models that I've shown you today are such that the arrest mechanism stems from the repulsion between the particles, right? But we can actually devise other models where the arrest comes from other types of mechanisms. And interestingly, you can show that you can map exactly into the same sort of hydrodynamics, which led us to speculate that there is indeed a broad class of a system which map into a similar phenomenology. So let me just show you one to conclude. This is a horny bee. You can find these bees in Southeast Asia. And what these bees do is that they can, when they see a predator, they can shimmer. So it means that you can have bees which are just sitting on the nest, which are here shown with bright colors. And then when they see a predator, they can hum their back, which corresponds to this black color. And what I would like to argue is that these sort of patterns are not captured by the standard complex Ginzburg-Landau equation. This is really an instance of what we call pulsating active matter. Why is it the case? Because here you can identify an arrested state, a background, if you wish, And the wave is really an excitation on top of this background, right? So specifically, you see the distribution of phase around this defect is not uniform at all, right? This is much more like what we saw here, where if you look at the distribution of the phase around the defect, you have clearly the presence of a phase which dominates over the other, which comes from the arrested background. Right. So let me conclude here. I would like to acknowledge all the people who have been involved in these works, which are mostly postdocs and PhD students from the University of Luxembourg. And thank you very much for your attention. I'll be glad to take questions.
So let's start here.
Yes. Thank you. So do you understand why the symmetry, or how this, you know, you have a version of CGLE with an additional f of a term that somehow has, doesn't have the rotational symmetry?
Yes.
Do you understand why the hypothesis of your model lead to that term? And if you would take our other hypothesis, what kind of other term would you have? Like, could you like think in terms, like broadly in terms of, you know, a relationship between the ingredient of your model and the symmetries of the equation that you get at the end? Is it possible?
Yes. So I guess, well, hopefully what is clear at this stage is that, you know, if I go back to these microscopic equations, right, the fact that you have a repulsion is directly what will lead you to have these extra terms, right? Hopefully this is, let's say, the zeroth order of understanding of these theories, right? Indeed, you see, if you kill these terms, so if you kill the repulsion and the system is dense enough, you have essentially a Kuramoto model, right? And if you have a Kuramoto model, not so surprisingly, you get back to the standard CGLE. Yes. So this would be my order 0 argument, which is that you need here repulsion to arrest the dynamics in order to yield these terms, right? Does this? Can
you break another symmetry? Do you know which term you should use your model to do that?
Can I break another? Okay, so maybe a way to answer that is, okay, so there is a version of these pulsating active systems where, for instance, you have particles diffusing on a lattice, and each particle can only be in one of 3 states. And interestingly, here you can assume that from the perspective of the position, it's a free gas of particles, right? So there is not any repulsion between the particles, right? But the fact that each particle can only cycle over a finite number of states, you can show that this is actually enough to arrest the dynamics. Okay. Now going back to your symmetry argument, you can show that actually in this case, although you break the invariance under a continuous symmetry, you still respect the invariance under rotation by 2 pi over 3, right? Because you have symmetric states, right? So maybe that's going in your direction. And in this case, you can show actually that to this, to the 3rd order in powers of A, the only term which breaks the continuous symmetry but respect the discrete symmetry with respect to 2 pi over 3 is the complex modulus of A to the power 3. Okay, so you can try and play these games now, which is try to understand what will be the minimal terms which break the continuous symmetry but which maintain some other symmetries, and then you could try and study these equations by their own. Yeah, I guess this is answering your suggestion.
Yeah, I have a somewhat stupid question. What is the origin of chirality? Is there a simple way to introduce chirality in your model that you showed towards the end?
I'm not sure what you have in mind by chirality there.
In that the excitations that you see has a certain handedness. The simulations that you showed later on did not have that, right? So
you mean perhaps it's sufficient to argue that the drive itself induces in chirality. That I guess would be along the direction of what you say. Yes, it's true. This is not a feature that we study very carefully in the sense that, for instance, when you have spirals, because you need to conserve the total charge, right? Even if you have a spiral which has a given handedness, you need that another charge with the opposite sign in order to conserve the total charge, right? So I would say the drive is important just from my perspective to drive the system away from equilibrium, right? But the fact that this omega has a given sign or the other would not impact so much the phenomenology here in this model. Yes.
Sriram.
Yeah. You know, you, as motivation, you talked about fibrillations in cardiac tissue and so forth. There's a big literature on that, which largely ignores mechanics and only looks at electrical excitations and voltage, the coupled dynamics of voltage-gated channels and Kirchhoff's law, effectively, right? And I've often asked my friends who work on this why they don't worry about mechanics, active, etc. On the other hand, it seems to be a growing business in which they don't seem to need to worry about it. So do your findings, tell us that we should be thinking more about this aspect, or is that field perfectly happy as it is and you just, what's the status of this and what do you think will happen as a result of these findings?
Well, thanks very much for this question. Indeed, it's quite relevant. So, okay, first, what do we say that the other models cannot say? Well, we say that, for instance, to go from a defect turbulence to these sort of patterns, which will be respectively going from here to there, right? So this, a sane heart is a heart which has a planar waves, which has a clear direction in order to contract right and then left, and this is how you pump. When you have these beautiful patterns is when you should start to seriously care about your health, because although it's beautiful patterns, it's not going to pump any blood anymore. To go from here to there, you just have to reduce the density. Right. That's the first thing we observe. This is something you see very clearly in this phase diagram, is that the defect turbulence is around here, and then as you decrease density, you go towards spiral and towards, I would say, a saner rhythm for the heart. This is the first obvious control parameter, but if you ask a medical doctor, can you please change the density of the heart?
Well, yes.
He might not take you very seriously. But something you could argue is that maybe another control parameter which might be relevant for your question is this one, which is essentially the deformability of the cells. We have not investigated this in great details, but this is something that in this context would be interesting. Now something that, in particular in the context of identifying the dynamics between the defect I've shown you at the end and how they organize the pacemakers, right? You would like to dream that a simple way to cure the emergence of defect turbulence would be to have pacemakers, several of them in the tissue, right, which could essentially mitigate the formation of defect turbulence, right? And this is more about the idea of control the system when it forms the patterns, please mitigate it and go back to another.
I mean, at the moment, there is a control strategy, which is brutally introducing scarring of various sorts. No, that's an immediate, what you're talking about, those paddles is an immediate reboot. No, I'm talking about, they actually introduce scar tissue inside the heart to, to prevent spiral growth and so forth.
I see. So
anyway,
this is,
we can talk more. Right?
No, this is actually very much like what you find in crowd control, for instance, in a concert.
Sure.
Right.
Okay. Anyway,
thanks.
I think go on the other side first.
I had a question about the location of these pacemakers. Why do they remain pinned? I mean, if you had noise, would you not expect them to diffuse eventually?
No, they do diffuse very much eventually, yes.
Okay. That's just on a longer time scale then.
That's right, exactly, yes. So there's what we argued is a hierarchy in the sense that these, for instance, asters have a longer relaxation, but the pacemakers themselves evolve a lot. Yeah. So what I was trying to show you with this movie here is the fact that the first stages, right, of the pacemakers are very much determined by the early instability. But then there is a longer relaxation process where you see you go from many pacemakers to only a few of them, right? This is already quite a relaxed state, probably not a steady state, but you see already here there is clearly a symmetry which says that to attain that, you have to wait longer. Yeah.
And how does that coarsening process work? Does that fall into any of the usual sort of model A, model B coarsening type classes, or is it something completely different? Do you know?
Very good question. We do not know. So this would be a model C if you have no drive, right? So this would be two scalar fields, one conserved, the other not. Sometimes of strange magnets, you could argue. But how the coarsening happens in the equilibrium itself, I don't know. And how it's affected by the drive, that's a very good question. We still don't know.
Thanks.
Olivier?
Okay, thank you for the talk. I have two questions. a bit aside, leaving the heart aside. So one is about your CGL equation with this broken gauge invariance.
Yes.
So, I mean, aside from what you described, if you compare the dynamics of this CGL with the one where you have gauge invariance, did you look at it a little bit systematically? I mean, there is all this literature on CGL, and what are the main effects of breaking this gauge invariance?
Yeah, thanks, Olivier, for this question. So maybe something I should emphasize is that if you, for this specific CGLE, so first it's really one instance of the CGLE in the sense that, for instance, here D, the diffusion coefficient is actually real.
Yes.
Right? And you can, so if you think of the CGLE, for instance, being a field realization of a Turing model, if you have a real diffusion coefficient, it means that you have the same diffusion coefficient for the two species, and you know this is quite bad to create patterns. You should typically have different diffusion coefficients. And in this case, you can show actually that also A and B are constrained in such a way that if you kill F, actually you don't have any patterns in this case. You just have order disorder transition.
Okay.
So in that respect, the CGLE limits, the limits where you kill the repulsion is a bit trivial. And this is actually, so I don't have the phase diagram here, but this is, right. So you see here, there is also a pocket of disorder. Right? So there is a whole part of the phase diagram at low density, which we call the trivial part, which is the part where essentially the phase boundary does something like that. And this is something you get at mean field level. It's just epsilon times rho equal noise, which is the standard Kuramoto model, right? So if you kill the repulsion, in other words, if you kill the breakdown of rotational invariance, all these interesting parts are essentially going to higher density and they disappear, right? Okay. So this is a subpart of a broader phase diagram, and what happens if you kill the repulsion is that the broader phase diagram invades this part.
Okay, and so my second question is related to Kuramoto. So here the omega, the forcing is delta.
Yes.
And of course the question is what happens if you have a distribution of omega, so disorder, like in the original...
Yes, very good question. We do not know. Indeed, that's something which could be explored. That's something good. I have no intuition. I think, in practice for the Kuramoto model, if you have a distribution of frequency, it affects the order disorder transition.
Yes.
Right? But again, I think it would probably affect, it would change this transition probably. My guess would be that this is quite robust with respect to a distribution of frequency, but I might be wrong.
Okay. Thanks.
Last question.
Thanks. So first, do I understand correctly that the driving is constant everywhere in time and space, right?
Yeah.
And so normally when I think of driving, I think of burning free energy in order to drive the system out of equilibrium.
Yeah.
But it's kind of obfuscated here because there's interactions and phases and so on. And of course, when I think about an actual heart cell, it's only consuming energy in a particular location. So is there a way of being able to dig deeper into some sort of actual microscopic free energy consumption?
Yes, there is.
It exists.
That's it.
No, I was... No, there is definitely. That's what we're trying to do now. But I guess the question you ask is, can you build the energetics of this model? Can you understand what is the amount of dissipation which comes with sustaining such patterns? Can you, for instance, perturb the system and understand what is the relation between work and heat? Yes, the reason why I was taking a bit of words, because this is something I've been doing a lot on other models of self-propulsion, and which interestingly triggers quite a lot of debate, because it's easy to understand what is the work associated with the perturbation, but understand what is the heat requires quite a few constraints on your model. And one of the biggest criticism that you receive if you work on the energetics of active matter is that you have actually to have a thermodynamically consistent model. What does it mean? It means that you have to be able, along with what you say, to determine each time you have, if you think now of a Markov process, you have to be able to determine each time you undergo a transition, right, what is the amount of chemical potential difference, for instance, that you have to burn to go from this state to the other, right? What I'm trying to argue here is that this is a very interesting question, but probably this model is not the best fit to answer that. A way to answer a question would be, for instance, to take the lattice model, which I was suggesting when answering to Corentin, where you have particles on the lattice, and here transitions, you can count them one by one, right? And here you could have what we call a thermodynamically consistent version of this model on the lattice, and here you can study dissipation. This is very much something we're trying to do now, which is non-trivial, but maybe to argue that this is, again, a very good question, I think something we'd like to investigate very much is when you see this phase diagram, what is the dissipation associated with each time of these phases? Also, when you have patterns, can you have a local measure of dissipation, right? And we hope to achieve this question. Something we hope also to achieve is to think about control, which is, for instance, if you are in one of these phases, can you go to the other one in finite time? You know, for an equilibrium system, the best way to do so is always to drive as slowly as possible. For an active system, this is clearly a bad strategy, because if you wait long, you dissipate a lot, right? So you see clearly that if you plot your optimization function of time, if you are too slow, you dissipate a lot. If you are too rapid, you dissipate a lot. So there is always an optimum here, right? So a lot of things which we are doing, which is not about specific model, but broadly it's trying to understand control of active systems. This is something we are very much working on at the moment. This is something we'd like to deploy in this specific case, but I would say perhaps in another variant of the model. Happy to discuss more if you're interested.
All right, I think we're well on time, so we thank Etienne again. We go for the coffee break.